Swayam Prabha. Digital India. Educated India.
Welcome to my course Non-Metallic Materials, and today we are in module number 9, characterization of structure, composition and microstructure of non-metallic materials, and this is lecture number 45, where I will discuss the thermal analysis. So, various types of thermal analysis first will be introduced, and then we will concentrate on thermogravimetric analysis, followed by differential thermal analysis and differential scanning calorimetry. These two important characterization tool will be described, and various application that is possible using this thermal analysis that will be covered in this particular lecture. So, basically in thermal analysis, enthalpy, heat capacity, mass and coefficient of thermal expansions, they are measured as a function of temperature and in some instances as a function of time. So, in thermogravimetry, that we record the mass of a sample as a function of temperature and time. In differential thermal analysis, the difference in temperature between a sample and an inert reference material, that is measured as a function of temperature. In case of differential scanning calorimetry, it basically allows a quantitative measure of the enthalpy change that occur in the sample. In case of dilatometry, the change in linear dimension of the sample with temperature is recorded. For polymer based sample, this kind of measurement is also termed as thermomechanical analysis. So, a typical thermogravimetric analysis where a decomposition reaction is taking place, there the samples are heated in a constant rate. So, typically 1 to 20 degrees Celsius per minute rate is used. So, if you can see this figure, you can see the temperature of initiation of a decomposition reaction. This is here, and it ends at a temperature which is marked as T fin, right. So, initial weight was W init and the final weight after decomposition is W fin, and the difference in weight del W, that is measured. Basically, this weight change at each temperature is measured. The weights and weight difference, they are used for quantitative estimation. Either absolute weight you can use or the difference in weight you can use. So, there are various types of presentations, sometimes weight percent weight loss, that is also used in the ordinate. And the initial temperature T init and T final, if T fin, that is dependent on the heating rate. It is also dependent on the particle size of the material that you are using, and more importantly, it depends on the ambient that is kept surrounding the sample. If you consider the decomposition of calcium carbonate, T final will be the temperature where there will be the weight loss completion, carbon dioxide completely goes away. So, it depends on the nature of the ambient. So, if you do the same experiment in vacuum, see it is about 500 degrees Celsius where all the weight is stabilized. So, it forms calcium oxide. But if you maintain a pure air ambient, then this temperature increased, and if you maintain an ambient which is carbon dioxide at 1 atmosphere, this decomposition temperature is shifted to very high temperature, about 1000 degrees Celsius. So, it is important, you will have to report that at what particular ambient this kind of decomposition reaction is taking place. Another important thermal analysis is differential thermal analysis. So, consider your sample you kept in a crucible, and you have a thermocouple here kept, and you are increasing the temperature of this sample. So, sample temperature Ts is increased, and you have only the configuration is something like this. So, when a constant heat at a constant rate this temperature is increased, say melting takes place at some temperature, say at Tc, this is the temperature melting takes place. So, while the whole of it will melt, the temperature will remain constant, it will take latent heat, so it will remain constant. So, this will not change. So, there will be some kind of anomaly at this temperature, and again when this reaction is completed, then it will again catch up this heating rate. So, it will just be a change in the slope. So, sometimes this slope can be spurious. So, you cannot really identify that this melting transition at what temperature it takes place. So, it could be a spurious change in the slope. So, you can misinterpret the data. So, therefore, this differential thermal analysis is important, where you have your sample and along with that you have an inert material which does not undergo any kind of reaction, be that decomposition or whatever, I mean no reaction is taking place. So, it remains in its pure state, there is no phase transition, no polymorphic phase transition, nothing is happening to that. And then you connect the thermocouple back to back, and you measure the temperature difference as a function of temperature by putting another thermocouple inside the DTA equipment. So, del T is measured along with the furnace temperature. So, endothermic and exothermic events can easily be identified, because in case of say melting or in case of crystallization, then there will be either an endothermic reaction or it will be an exothermic reaction in case of crystallization. So, that can easily be identified. Now, you can get for example, in case of endothermic reaction a peak something like that. So, it is having an initiation and it is a completion. So, usually it is difficult to identify sometimes the initiation peak. So, the reaction can be characterized by the completion peak and you can identify this kind of transition. So, another similar kind of thing is differential scanning calorimetry. So, these are routinely used for various types of measurement of thermal events, including melting, crystallization, glass transition, some kind of curing reaction, decomposition reaction. So, usually about 20 milligram samples are kept in one of the crucible inside a DTF furnace, and the temperature range can be quite wide, maybe from minus 120 degrees Celsius to 600 degrees Celsius. So, heat needs to flow to the sample than to the reference to maintain both at the same temperature. So, DSC can be used to detect the heat change occurring during the chemical reaction. So, the graph this that explains the phenomena which cite a melting reaction of a metal which is occurring at about 158 degree Celsius. So, if you have the T versus T curve, this is heating curve, temperature versus time, before and after the melting it is linear, it maintains the constant heating rate. But the sharp change in the heat flow in case of DSC. So, here it could be just some kind of anomaly, but here there is a sharp change in the heat flow that actually identify very clearly the melting transition. So, the rate of heat flow dq by dt, that is dq by d temperature into d temperature by d time. So, the first one is the specific heat and second one is the heating rate. So, when a thermal event takes place, then your rate of heat flow change with time, that is Cp into the heating rate plus some thermal event phi. So, that denotes the heat flow change. So, TG, the thermogravimetric analysis that can detect only the mass change, but your DTA and DSC, they are more versatile. So, in some of the equipment, the thermogravimetry and the differential thermal analysis, they are used in combination. So, both are combined in a single equipment, and that is quite versatile in nature. So, here for example, you can consider the decomposition of kaolin that is taking place. So, mass change due to the decomposition is identified at a temperature about 550 to 650 degrees Celsius. So, the sample is dehydrated and DTA shows a very broad peak which is endothermic in nature in the said temperature range. But in addition, in case of DTA, you can see the presence of another peak. So, this is an exotherm which is otherwise there is no signature in the thermogravimetric analysis. So, the second exotherm at 980 degrees Celsius that correspond to the recrystallization of the dehydrated kaolin. So, this signature you will not get in thermogravimetric analysis because there is no mass change is involved in this crystallization, but DTA can detect it. So, DTA is in addition to the thermogravimetric analysis, it can detect additional thermal event in the sample. So, in some cases it can be employed to separate the reaction which is reversible thermal event from the one which is irreversible. So, in this particular schematic we have included the schematic of a hydrated material. So, in the heating cycle you can see endothermic dehydration, then a hypothetical polymorphic phase transition. Already I described in certain material the crystal structure changes, but this can be displacive or this can be reconstructive in nature. And then there is a melting transition. So, three types of reaction that you can see it is occurring here in the heating cycle. When you cool it, then this melting transition is replaced by solidification, and then the polymorphic transition, it is displacive in nature. So, again there is a signature for this, but dehydration is a irreversible phenomena. So, it cannot be I mean this is not appeared here. So, it can detect the reaction which are reversible and which are not reversible. so easily from the DTA relation. Here you can see little bit of hysteresis. So exotherm on cooling is usually shifted to lower temperature, that is marked by this arrow. So as compared to this temperature, it is shifted. And usually this kind of hysteresis is a very strong function, the amount is a strong function of cooling rate. So consider the glass formation that already I have taught. In case of crystalline quartz, the melting yields and endotherm, right. On cooling, the melts, they do not crystallize. So instead they become supercooled in nature. So crystallization is a slow event at slower cooling rate. So remember the concept that I talked about in the critical cooling rate is involved. So you cannot see the crystallization peak here in this case, in case of glass formation, but a broad anomaly is actually shown in the cooling curve, and this temperature is known as glass transition temperature, where the viscous supercooled liquid that is transformed into a solid glass. So this is the upper temperature limit at which the glass can be used. Already we talked about it. So this is this temperature is used to characterize the glass. So that is the limit when you consider in the heating cycle. So after that it transforms into a supercooled or uncooled liquid. So that defines the temperature till which you can safely use the glass. So these things can be detected by a differential thermal analysis plot. So silica glass, they do not devitrify. So once you melt it, then you cool it down, it will not crystallize back. So a broad anomaly only you will see that will correspond the glass transition temperature when you are cooling from the melt. But if you talk about the metallic glass, it devitrifies. So you can see in case of metallic glass, again you have the signature of glass transition, and then there is an exothermic peak. So that corresponds to the crystallization, and once you again further heat it, then it starts to melt. So faster cooling is adopted to avoid such devitrification. So in fact, if you cool the metallic glass from its melt at a very high rate, then only you can get rid of the crystallization phenomena, the devitrification. So other type of glass forming material, they are amorphous polymer and also in some cases amorphous chalcogenide semiconducting materials. They also form glass, that already we talked about while we I taught the glass in part of my earlier lectures. So the thermal analysis, the polymorphic phase transformation, identification of those polymorphic phase transition and control of the material property, DTA is a very important characterizing tool. So polymorphic phase transition, as you understand, it occurs in case of silicon dioxide, zirconium oxide, and usually they are detrimental for their refractory property, refractory based property because of the volume expansion. So this phase transition temperature can be identified by differential thermal analysis. Now you can use suitable dopant. If you remember, in case of silica, you can use certain dopant. In case of zirconium oxide, you can use yttria or calcia doped ZrO2 or various rare earth also can be used. so that this kind of phase transition is avoided. Maybe in case of zirconia, at room temperature cubic phase can be stabilized, which will not undergo any kind of polymorphic phase transition. So, that is good for the property that these materials are used for. So, in those cases DTA is absolutely necessary. Another important material of concern is barium titanate, which is used for dielectric material. So, here also polymorphic phase transition takes place, cubic to tetragonal, already we talked about it. Now, in case of this polymorphic phase transition, that transition temperature, the dielectric constant maximizes, right. So, you would like to reduce this transition temperature down to room temperature, because otherwise 120 degrees Celsius, where this cubic to tetragonal phase transition takes place, that is too high. So, you can use some kind of dopant like strontium replacing part of barium to form BST to reduce the transition temperature very close to room temperature by adding a specific amount of the dopant, so that the dielectric properties they maximize at room temperature instead of 120 degrees Celsius. So, for this kind of analysis DTA is very important. Another place where this can be used is the formation of cement. So, in case of cement, usually this alpha calcium silicate Ca2SiO4, that can either be transformed to a beta phase, beta calcium silicate, or gamma calcium silicate. Now, the beta phase, this is having better cementitious property as compared to the gamma phase. So, usually various dopants are used to stabilize this phase when it cools down from the clinker to room temperature. So, this transition or the usefulness of this dopant controlling this phase transition, that also can be studied by this differential thermal analysis, the transition temperature. Silica refractory, you know, the reversible alpha to beta transition that introduce lot of volume change. So, this volume change affects their mechanical property, as I said. Again, DTA can be used to study this phase transition behavior, or whether at all they are suppressed by adding dopant. So, it is indeed very useful. This is a very powerful technique to determine the phase diagram. This also I have taught in my other lectures. Now, how to make this kind of phase diagram. Along with X-ray diffraction, the DTA can be used to construct this phase diagram. So, here a simple eutectic phase diagram you may remember that is considered here. So, if you consider the composition A, then it basically melts at a temperature T2. So, when it melts, then it indicates an endothermic peak, a broader endothermic peak. But here you keep on heating it. So, there is a phase mixture of X and liquid, and finally the liquidus temperature is reached. So, then again the solid phase, they are all transformed to liquid phase. So, another endothermic peak it will appear in between T2 and T1 if you are having composition something like this, something like A, right. So, an estimate of both solidus T2 and liquidus T1 temperature can be made, and this can be made at any of this composition, right. All this composition you can mix in different proportion and do the DT analysis, and you precisely get the temperature. One temperature will be fixed and another one will be varied, and you will get this two temperature very precisely. If you consider the composition which is B, so this is a eutectic composition. So, in here this two solid will directly be melt and form liquid. So, only one kind of endotherm, which is the same temperature T2, it will appear here. So, DTA trace for a range of mixture between X and Y, they are compared, and also the polymorphic phase transition on the phase diagram that can appear at the sub-solidus temperature. So, if something is happening here, any polymorphic phase transition takes place, so that also can be identified by the DTA analysis. So, in other words, with the help of X-ray to know the exact phase composition, at least in the solid state, you can precisely get the phase diagram constructed by this analysis. Now, the baseline, not always the baseline is very straight. So, sometimes the baseline is also sloping. So, if it is a sloped baseline, it is basically related to the crystal disorder. And in modern DTA and TGA analyzer, there is in the software you can change the slope, you can cancel the slope. The decomposition pathway of a particular material that also can be identified, for example, by a TGA analysis. Here you can see that calcium oxalate hydrate, if you take, then it precisely they are decomposed to form three different types of material. So, it basically occurs in stages. So, first a anhydrate forms, then it transforms into a calcium carbonate before it finally converts to calcium oxide. So, this temperature corresponds to these reactions, they can be precisely identified by thermogravimetric analysis, for example. For certain case, a kinetic analysis also can be done in certain material. So, in this case, either you can raise the temperature at that particular temperature of concern where the reaction is taking place, and then for example, in TGA this material is directly inserted to a temperature where a decomposition reaction is taking place, and then you can start measuring the weight as a function of time, right. So, various temperature you can select and then directly insert your sample right at that temperature, and the weight transient you can measure in isothermal condition, and this data can be used to determine various kinetic parameter which is occurring in this reaction. Alternatively, a single dynamic heating cycle at various heating rate also one can use to determine the reaction mechanism, and from this one can precisely determine the type of nucleation and growth, whether it is Avrami type or some other type, what is their activation energy. This can be very precisely known by this kind of kinetic analysis. So, if the equipment is suitably calibrated, DTA is also used, although it is semi-quantitative way. Enthalpy of transition of the reaction, and usually it is found from the area under the peak, which is not part of this lecture. So, that also can be used to measure various other material related parameter, which is helpful to understand the reaction mechanism we are talking about. So, the study material for this part of the lecture is the book by West, Solid State Chemistry and its Application, chapter number 4. And apart from that, you can consider the material characterization technique by Zhang, Li and Kumar, and the other references that I have cited here. So, in this particular lecture, the principle of thermal analysis used for non-metallic materials are introduced. Specifically, the principle of thermogravimetric analysis, DTA and DSC we have introduced and described, And in particular, the various applications of TG and DTA we have highlighted, the thermal events, reversible reactions, the concept of hysteresis, why it is forming the hysteresis between the cooling and heating cycles, the temperature difference. Then application in glass formation, polymorphic phase transition, controlling the properties, how they are used, and finally kinetic analysis that can also be done using the DTA and TG measurement, and we have talked about it. Thank you for your attention.